Okay, so our first talk of this afternoon session is by Yiming Chen, who's going to talk to us about dynamic behaviors of a Leslie-Gower model with strong Allee effect and fear effect in prey.
All right, thanks. Okay, first I would like to thank the organizers, Chen and Shigui and Jianhong for the invitation to give a talk here. And on this important event, to pay our respect to Gail. I think I met Gail possibly in my graduate studies, but I'm kind of, at that time, I was not too active, possibly I don't interact with people too much, but I think what the occasion I remember clearly is in 2002, I think we 4 feminists, Gail, Suhan, and Jianhong, we went to Africa safari. Now the kids have grown up, and luckily we are still healthy and still see each other around. So happy birthday, Gail, and also thank you for your help or assistance during my academic development, and also, of course, for the assistance for the other people like Suan, Shigui, Xinhu, and Xiaoqiang. Okay, so today I'm going to talk about the Leslie-Gower model with strong Allee effect and fear effect in prey. So, of course, in the previous lectures, we have some people have mentioned the Allee effect, and so here, I'll give you explain a little bit about the Allee effect and fear effect. So here is the outline. So we are first we are introduce the model, and then we are give some preliminary results. So show the origin is a attractor, then we consider the existence and the stability of equilibrium. These results indicate some bifurcations, and then we conclude the talk with some summary and discussion. Okay, so of course, lots of us knows this predation. So predation refers to a flow of energy between two organisms, the prey and predator. In the interaction, the prey loses energy and the predator gains energy. There are 4 major types of predation. So carnivory, herbivory, and parasitism, mutualism. So the carnivorous predators kill and eat the prey. The herbivorous predation involves the consumption of some autotrophs such as the plants or photosynthetic algae. So unlike the carnivore predation, so not every herbivore interaction leads to the death of the plant. And the parasitism, so in this interaction, the host supplies the essential nutrients for the sustained survival and the reproduction of the parasite. And usually, of course, the host is not killed. And during the mutualism, so the host provides the nutrition and space for the growth and the production of another species. And in this interaction, we know that usually the other species didn't do any harm to the host, and the 2 species are mutually beneficial to each other. So, and we know that this predation is ubiquitous in nature, so there are lots of studies about it. And of course, since the seminal works of Nautaka and Watara, this classic Nautaka-Watara model, so has been modified in many ways to account for the various observed phenomena. So one of the modification is the following one, so described by this ODE. So it's called the Leslie-Gower model. So here XT and YT denote the densities of the prey and the predator at time t respectively. One feature of this model is that for the predator, so it also follows the logistic growth. So with the carrying capacity Nx, so which depends on the abundance of the prey. And here N so measures the quantity of the Poiret, and nx is called the Leslie-Gower term, and of course px. So here you just use the simple function response. So it's only Poiret dependent. So, and of course, in the previous some lectures, we have seen that the function response, of course, affects the dynamics very much. So, of course, this model has been studied by many authors. Here is just a few of the references. What we mentioned, so for the predator-prey models, so there are lots of factors affecting the dynamics. So one, like the functional response, but currently two factors involved. So a lot of people have studied the influence of the Allee effect and the fear effect on the dynamics of predator-prey models. So the fear effect of predators is a form of indirect predation impacting the prey population. So to some extent, we know that the physiology states of the prey are disturbed by the fear effect. So yeah, well, the result in the long run, so they cause some loss in the growth of the prey population. Meanwhile, we know that the prey suffered from the fear effect usually will foraginess, and then their growth rate will decrease, which is not good for the survival of the prey's population. So it is necessary to incorporate the fear effect into the predator-prey interaction. And so in 2016, and so Xinhua and Xiaoyin and another one, so they modified the fear, firstly modified the fear effect by introducing the factor FKY, so which exhibits the cost of anti-predator defense due to fear of our predator-prey system. And also this K just represents the intensity of anti-predator behavior of the prey caused by fear. So this paper, I think, since its publication, has been well recognized, and there are lots of follow-up of it, and even some people working with the reaction diffusion equations. So I think it has more, it's about 200 citations already. I won't go too much about the fear effect here. So a recent experiment designed by Iliad demonstrated that the Allee effect can be induced also by the fear effect. So let's talk about the fear effect. So the generally accepted definition of Allee effect is the positive density dependence or the positive correlation between the population density and the individual's fitness. So the Allee effect appears due to a wide range of biological phenomena. So for example, the reduced anti-predator vigilance, the social thermal recognition, genetic drift, mating difficulty, reduced defense against the predator, deficient feeding because of low population densities, and so on. So there are lots of ways to classify the Allee effect. So they can be classified as component Allee effect or demographic Allee effect. So here I just mentioned the democratic one. So a democratic Allee effect means a positive relation between the overall individual fitness and the population density. So if there is a critic population size or density, so this is called the strong Allee effect. If there is no, then this is called the weak one. And this is the general one where there is no Allee effect. So here are some of the common used Allee effects. So based on the logistic growth, we have the quantitative any effect. So you can see this is just another factor x minus n into the standard logistic equation. And there's the additive any effect. So the modified system here by input this m over x plus b. And of course, there are other forms. For example, by assuming that the fertility depends on the population size due to any effect, Zhu and Mimura, they propose this one. And also to account for a higher extinction rate on small populations than in other modern approaches, Boca and Piri, they propose the following one for the any effect. So this one here, you can see the another term here is factor here. So this one we are kind of modify the intrinsic growth rate. Okay. So for the Leslie-Gower model and the modifications, usually there are some ones like using different functional response, or you can see for the Leslie-Gower model, you have this singularity there. You have an nx at the bottom, so some modified it with a constant plus nx. Then there are lots of studies of these models with any effect. So here are some revisions for models with additive any effect, and here are some others with cognitive any effect. Of course, the obtained results indicate that when you have the any effect, so these models will exhibit very complex dynamics. So our modification of the model here is as follows. So first, based on the experimental observations of Ineos, then SESMA, they proposed and investigated the following model here. So with the any effect and also the fear of effect, here theta and f are the any constant and fear factor respectively. They showed that the fear effect has no influence on the stability of equilibrium. And on the other hand, Gonzalez, omnivorous, and his collaborators, they studied the following Leslie-Gower model with any effect in the parade. So this is a strong multiplicative any effect. Of course, for the model, if there is the function response here, you can see it's quite simple. It's just a bilinear functional response. So we know that if there is no any effect, the model has a unique positive equilibrium, which is globally asymptotic stable. However, with the presence of the strong any effect, the number of equilibria varies with respect to the any effect threshold, and also the model exhibits local bifurcations, including Harpur bifurcation and the Bogdanov-Tekin's bifurcation. Okay. So our purpose is to consider if we incorporate the any effect and also this the fear effect with the Leslie-Gower model, say what kind of dynamics we will have. So we will study the following model. So here all the parameters are positive constants, and also we assume that any effect threshold is less than the carrying capacity. So first, for the convenience of analysis, so we non-dimensionalize the system. So we introduce the new variables and scale the time. Then if after dropping the bars, we get the new system. So then, of course, you can see we have a restriction on the parameter m. So it will be between 0 and 1. So if for this model, as we just mentioned, because you have this singularity here, means that when x equals 0, there is no parade. The system is not defined here, but we know that the dynamics when the parade is very small is very important in ecology. So in order to study this dynamics there, So we are further rescale the term using this scaling here. Then we can change the system into this system. So this one is very nice. There is no singularity. For this system, we'll see that it will converge much faster to the equilibrium than the original one. And also, this time scaling here will not affect the qualitative structure of the original system. So in the following, we are only focused on this transformed system. So for this system, of course, this is very standard. So because of the biological background, so you consider initial conditions in the first quadrant. Then, of course, for each initial condition, you have a global solution which stays in the first quadrant. And for this model, so first we usually have to consider the real positiveness, means that whether the solution is bounded or not. And in fact, we can show that for any solution of the system 1.4, they are uniformly bounded by 1. And of course, this is not difficult to obtain. So just using the differential inequalities. And so as we said, so this means that the system is well posed. And now you can consider what happened to the origin. Unfortunately, the linearization is inapplicable in this case because the Jacobi matrix at the origin is just a 0 matrix. So to get the qualitative property of the origin, so we use the follow-up method. Then with it, we can show that the origin is a non-hyperbolic attractor for the system 1.4. Okay, so now we come to the equilibrium. So of course, the equilibriums are determined by the solution to the algebraic systems. So you can easily see that the system always has two positive boundary equilibrium, P1 and P2. And also you can see any positive equilibrium has the form of XX and X satisfying the quadratic equation. So from the quadratic equation, you can easily see it depends on this coefficient of the linear term. So if the coefficient is non-positive, then the 3.1 has no positive roots, and hence the system 1.4 has no positive equilibrium. Now, if you assume n minus q plus 1 is positive, then you consider the discriminant of this quadratic equation. You can regarding it as a function of a function of n is a quadratic function, then you can easily see that it depends on the value of your q. Right? If q is less than or equal to 1, you can, because we mentioned before, your m is less than 1, and here your m is not q minus 1 because of this t. So you can easily see in this case there is no positive root for to 3.1, and then if q is between 0 and 1, then you can see you have two situations, right? Whether the discriminant is positive or is 0. So in summary, you can easily get the existence of equilibrium. So there are always 3 boundary equilibrium, the origin P1 and P2. And if you want to have the positive equilibrium, it's necessary that Q is between 0 and 1. Then it depends on your M. If M is between M1 and 1, there is no positive equilibrium. M equals 1, so there is a double unique positive equilibrium. And if it's between M between 0 and M1, there are 2 distinct positive equilibrium. Okay, so now we consider the equilibrium stability. So for P1 and P2, this is easier. So you can easily get the Jacobi matrices at these 2 points. And because M is less than 1, so you can easily see your P1 is a hyperbolic unstable node, and while your P2 is a saddle. So for P bar, we have the following result. So when P bar exists, so if S is larger than S star, a star is given by this formula. So P bar is our side node with attracting parabolic sector. And if S is less than a star, so this is here a side node, but the parabolic sector is repelling. And when S equals a star, then your P bar is a degenerate equilibrium. And furthermore, depends on if one of these two conditions is satisfied, your P bar is a cusp of codimension 2. But if these two conditions are satisfied, then your P bar is a cusp of codimension at least 3. Okay. Maybe so here is the phase portrait near this P bar. So here you can see this is the case. You have a cusp of codimension 2, and here is you have a side node with an attracting parabolic sector, and this is one you have a side node with a repelling parabolic sector. Let me sketch the proof. So again, so this time the linearization is in optical ether as the determinant of the Jacobian matrix is 0. So to get the quantitative property, so we first translate the equilibrium to the origin, and then you have this transfer the system 1.4 to this 3.2. And then you can easily say if S not equal to S star, so we use a non-singular linear transformation, and also consider the time scaling to transfer the system into this system. So then you can easily see this this coefficient is positive, and then you consider find out the center manifold. The equation on the center manifold, so it's approximated by this equation. Then we use the result from the book of Zhang. So we know that the degenerate equilibrium P bar is a side node, while the parabolic sector is located at the right half plane. Then also depends on the time scaling. So you can see when this, I think when S not as star is A0 plus A01 plus B01 is positive, so the parabolic sector is attracting. So when S less than S star, this number is negative, so the parabolic sector is repelling. Okay, so but when S equals S star, so you can see because this coefficient will be 0, so you cannot use the result there. You have to make further transformations so to get the result. So we use this transformation, transfer into here. Then you use the C infinity change of coordinates in a small neighborhood of the origin. So you get the normal form of this system 3.5. So here you have your F20 and F11, and F20 is less than 0. So we have to consider the sign of this F11. So when you analyze this, the sign of FF, then you'll get the result, and you know why the numbers there. I think 2 minus square root 5 or something. Where it comes into the statement of the result. Okay. Okay. So for the stability of P3 and P4, so you can easily see that the determinant of the Jacobian matrix at P3 is negative, and the determinant at the Jacobian matrix at P4 is positive. So for P4, so you have to consider the trace. So combine them, so you can get the stability. So when it exists, so P3 is always outsider, and but P4 depends on S. So it can be a sink, a source, or a center, or a fine focus. Okay. Okay, so from these results, you can see that the system can have some bifurcations. So first, we consider the side node bifurcation. So by theorem 3.3 and 3.4, we know you can find out the set node surface is given by this one here. So find the face of the set node surface, you can see there is a critic number for the any effect threshold. So when m is larger than m1, then from the point of biology, we know that Puri will face the risk of extinction. But when less than m1, the dynamic behavior of system 1.4 becomes complex. So because you can have a saddle or anti-saddle come out in the phase. So which means that if you want the prey to survive, so their density must be large enough. Okay. Also, you can see there by theorem 3.4, the log stability of P4 will change as the parameter S varies. Of course, you can have some other parameters changing, let it change. So this means that possibly you have the half bifurcation, so you can have the critical value as given by that, and that at here, so your trace is 0, and so your P4 becomes a non-hyperbolic equilibrium, and then you can verify the transversality condition, so which is negative. So this tells you that you can have the half bifurcation. So this is the result. So let S be the half bifurcation parameter. When S crosses the threshold value, so the system undergoes a non-degenerate half bifurcation around P4. Okay. In ecology, we know that the stability of the bifurcated limit orbits are important. I think in the talk by Gergenis, as I mentioned already, so for the stability of the bifurcated period orbit, so you can calculate the force Lyapunov coefficient. So here we do it by for this one, we are transform this equilibrium to 1,1, then using this transformation, then you can see that because this system has the equilibrium 1,1, so you have a same relation for the Q equals that, then other parameters will satisfy these conditions. Then if you replace Q with this expression, then you rewrite your system in this way, and then you only need to consider the dynamics near this equilibrium 1.1 for the purpose to understand the dynamic of the original system at X bar at P bar. So for this new system 3.3, so you can see that at this point value you have the Jacobian matrix has a pair of conjugate pure imaginary eigenvalues, and you can verify the transversality condition, and then you usually you need to find out the normal form. So you do some transformations. First, transform the origin to the origin, the equilibrium to the origin, and then you do this scanning again, the near non-singular transformation. So you get this one. Then you can find out using the result from the book of John, so using the formal series method, and with the help of Maple, so you can get the expression for the force Lyapunov coefficient. So it's complicated ones here. So of course, we know P4 is always positive. So the sign of P1 depends on the numerator. So you have the result. So if this numerator here is positive, then the system exhibits a subcritic half bifurcation around the equilibrium. So this is shown in this picture here. And if it's less than 0, so the system exhibits a supercritic half bifurcation at by P4 at S equals SHF. Okay. So you can see what happens if L1 equals 0 or L11, then you cannot if you want to know the stability, you have to consider the second Lyapunov exponent. And of course, the expression for the second Lyapunov exponent is very complicated, so we won't write it down. So we just show the possibility with numeric simulation. So we choose these parameter values. So you can find out that L1 equals 0, L2 is positive. So you can see that the system undergoes a degenerate hyperpolarization of codimension 2, and there are 2 limit cycles. There are 2 limit cycles here. You can see the outer one, the inner one is stable, the outer one is unstable. Okay. Finally, we consider the Bogdanov-Takens bifurcation of dimension 2. So by theorem 3.3, we know the P bar is a cuspal of dimension 2 when M equals M1, S equals star, and Q equals Q star, and phi F not equals 0. So if you, here we choose the any effect constant and the field effect constant as the bifurcation parameter. So if after obtaining the was unfolding of the unfolding system of 1.4, so this one here, so you can see we have this change here. So here your number 1 and 2 are disturbed in a small neighborhood of the origin. So we can confirm the occurrence of Bogdanov-Takens bifurcation around P bar. So here's the result. So if your phi F is positive, then the system 1.4 exhibits a supercritic Bogdanov-Takens bifurcation, which accompanies with the appearance of a stable limit cycle originated from the supercritic hyperbifurcation, followed by a stable harmonic loop. So if your phi F is less than 0, then this just changes it. So the supercritic change to subcritic and stable change to unstable. So you have a similar result here. So here is some of numeric simulations here. So we have the first case here. So you have the, we choose X bar, then the F, then you can find this parametric values. So here you can find that phi F is less than 0. So here is the bifurcation diagram. So you can see the side node bifurcation and the hyperbifurcation too, and the harmonic bifurcations. And here is some, so you can see if number 1, number 2 is 0.01, 0. So I think it's this one here. And this first region, then you can see there is no positive equilibrium. And if you change a little bit, so this one here, I think it is in the second region. So you can see you have an unstable focus and a saddle. And in this situation, so you have, this is for the harmonic, and the hyperbifurcation curve there. So you can see on the hyperbifurcation curve, so you can see you have an unstable limit cycle with a hyperbolic stable focus and a saddle. And this case, so you can see the harmonic bifurcation there. So you have a harmonic loop consisting of unstable harmonic and saddle when number 1, number 2 should be an unstable harmonic orbit. And so you have these values. And finally, for this parameter values, so you can have a hyperbolic stable focus and a saddle. Okay, so this is a case when your phi F is less than 0. So if your phi F is positive, so this is just the case. So you can easily see similar simulation. So you just reverse of the errors and so on. Okay. Okay, I think that's all of the theoretic and numeric parts. So in summary, so in this talk, we investigate dynamic behavior of a Leslie-Gower model with a linear function response and both field effect of predator and any effect in the prey. So our findings are as follows. So the origin, you can see, is our attractor. So of course, go to the origin system, so we are attracting. And so this means that if your prey density is very low, so then the system will collapse. And our theoretic finding analysis findings reveals the complex dynamics when you have the combined any effect and field effect. So you can see the number of equilibrium and their stability will depend on the any constant and the field factor, and you can have codimension 2 or 3 classical coexistent equilibrium, and you have various bifurcations bifurcations like side node bifurcation, Hubble bifurcation, and PT bifurcation. And also, if you compare our results with the two works which motivate our study, so if you compare with the work of Gonzalez and Oliveros, so they only consider the effect of the impact of any effect. So here we focus on the cost of the anti-predator response in the pre-reproduction. So we can, if you consider field ones, the field effects still doesn't change the stability of equilibrium. So these are the results similar. So these results are similar to the ones we have like this paper there. But if you compare the work with the work by Sesmer, so of course here we consider a Leslie-Gower model, and we can see that as any constant varies, the model experiences side node bifurcation, and there are at most 2 equilibrium in the phase diagram. And compared with the traditional predator-prey model, so the model here can undergo more complex bifurcations, the PT bifurcations. And also, of course, you can see you can have a subcritic or subcritic Hubble bifurcation, and even you can have the degenerate Hubble bifurcation. I think I'll stop here. Thank you very much for your attention.
Thanks. Do we have questions?